Hello everybody and welcome to the last lesson of chapter 2 of advanced functions. Today we'll be covering chapter 2.5 and 2.6 because they're solving the exact same problem in two different ways. So let's get started in that. Chapter 2.5 and 2.6 is focusing on solving polynomial inequalities. Chapter 2.5 solves them graphically, and then chapter 2.6 solves them algebraically. So when it comes to solving all types of polynomial inequalities, there's only one method that works, and that is to use graphing. In the last couple of lessons, we have been working with factorable polynomial functions. However, most of the time, you won't be dealing with pretty numbers in mathematics, and sadly, that's the reality. So when it comes to polynomial functions, you can easily have irrational roots, which cannot be found algebraically. That's when graphing comes in. In chapter 2.5, we focus primarily on solving polynomial inequalities by graphing them. This concept is extremely important to learn, however, it's probably not going to be tested on a test or exam at your school. However, again, it is still important to learn. In my personal experience, we were using graphing calculators to solve these types of questions, but since I can't actually use a graphing calculator and show to you the steps, I'll be using Desmos to illustrate the exact same type of problem we'll be solving. Make sure that you pay close attention to how to use a proper graphing calculator once you come back to school, because there are different procedures that must be followed, but essentially the steps will be the same. Just the way you follow them will be a little bit different. I'll be showing you how to solve some questions from chapter 2.5 on the next slide. Well, actually, I lied. On the next slide, I'll be explaining to you how to solve this question using graphing. I know, I'm a genius. There are a few important concepts you should remember when working with inequalities. First of all, a polynomial inequality results when an equal sign is in a polynomial equation is replaced with an inequality symbol. So instead of finding when a function equals a certain number, we're talking about a range where the function behaves in a certain way we want it to. So the zeros of a polynomial function, or the x-intercept of the corresponding graph, divide the x-axis into intervals that can be used to solve a polynomial inequality. Again, this is like the biggest concept you could learn from this chapter. Polynomial inequalities may be solved graphically by determining the x-intercepts and using the graph to determine the intervals that satisfy the inequality. For example, if your inequality is stating that the graph is less than 0, you have to find the x-intervals where the graph is below the x-axis. Essentially, what all you're going to be doing is entering an equation into a calculator and using various strategies to understand what the graph means, as I just said. Let's do an example on the next slide. So we have two inequalities here. We could see that they're most likely not going to be factorable, which is why I'm gonna bring in a graphing calculator. So here's my beautiful Desmos, and this is question 1. This is our graph. It's a great graph. What you could see is that these are the roots. Again, it's probably going to be a little bit difficult for you to find these exact values. That's why we're graphing it. And in our question, we were asked to find it when it is smaller and or equal to 0. So when it's smaller than 0, it's quite clear. It's over here, right? From the range of negative 1.6 to 0.8, and since it's smaller or equal to 0, this is the range that we get. On Desmos, it will signify if the points are included by using a straight line or like a full line compared to just a dotted line like you see here. So for the answer for this question, what we would say is that the function, let's say p of x, let it just say it's p of x, is smaller or equal to 0 when x is greater or equal to negative 1.621 and smaller or equal to 0.873. That would be our answer. now we have this equation here, which I already graphed. So you can see it immediately gives us the answer, but we can't really see what those values are, which could be a little bit of a problem. So what we should do is first of all rearrange this equation, right? So let's bring out these two to the opposite side. So you could do minus and then 0 here. So you can see you get the exact same graph. But now we can get rid of this and just graph that. That's our new function. Since we were talking about it being greater or equal to 0, we are looking at the intervals over here. So it is smaller than 0 between these two, which means that when the graph is smaller than negative 0.634, it satisfies our question. Also, when it is between 0 and 6.617, it is also greater than 0. This will be our answer. As you can see, once we go down, it looks like it's a fairly straight line, but it's actually going down and moving a tiny bit, so that's fun. As you can see, these answers are verified with the thing we had here. So all you have to do is learn how to analyze a graph for it to satisfy your equation. It most likely, I recommend doing this way a lot more, where you rearrange it. However, try not to divide by like an x or divide by like a -1, because that will usually affect your original function, which wouldn't be good, because then you get the wrong answer. Okay, with that, we're essentially done chapter 2.5. Actually, yes, we are done chapter 2.5 because that's how simple it is. It's just testing the knowledge of you knowing how to graph an equation and look at it and analyzing it. So let's move on to chapter 2.6, which involves solving factorable polynomial inequalities algebraically. Again, if a polynomial function can be factored, then it is possible to solve it algebraically. For a factor inequality to be solved algebraically, you have to consider either all cases or learn how to use intervals, and then test values. So when it comes to using intervals, you could use either tables or number lines to help provide a visual clue to the solutions. Also, for this part of the chapter, I'll be focusing primarily on how to use an interval chart to solve inequalities, as this method could also be used in calculus. However, I will explain what considering all cases means, as that is also a very important concept you have to understand before you apply the interval charts. Also, make sure to follow whatever your teacher says in class, as not every teacher follows the same exact method, and if you don't follow the method they've been using, you're not going to get a good mark. Okay, so there's a few steps to solve a factorable polynomial inequality. First of all, I like to, but you don't have to, especially if you're afraid of messing up. You could rearrange the inequality so that you have a 0 on one side. Usually that will let you factor everything a lot more easily. However, you have to make sure that you don't accidentally change the equation by like multiplying everything by 2 or things like that, because that will change the equation. Also, after you factor, you need to find the zeros of the function, which we know how to do now. You could apply the factor theorem to find the zeros. Next, what I like to do is set up an interval chart. So to set up an interval chart, you follow the following steps. Write all the factors down on the side, and then write all the intervals of the function using the zeros found. As we discussed before, the intervals could be found between the boundaries of the zeros. Say from 0 to like 1 is one boundary if the zeros are 0 and 1. Then what you would do is use a test value from each interval to find whether the function is positive or negative when substituted into each factor. So if our interval was from 0 to 1, could choose a number like 0.5, and then we'd substitute that 0.5 into each factor that we got. So if it was x minus 1, we would do 0.5 minus 1, which is negative 0.5, which is of course a negative. What you could do is just write down the negative portion rather than like the full value, as again, for the next step, all you're doing is multiplying the positive and negatives you wrote down, and then you're writing that value, or that positive or negative, as your answer for f of x. Then you're repeating those exact steps for all the different intervals you have. Again, we will do an example now for how this works. So let's solve the following inequality. Okay, so I have written down the question, and now let's follow the steps to actually solve it. So let's say let p of x equal to the equation, which is 6x to the power 4 plus x to the power 3 minus 8x squared minus x, and then plus 2. And that is smaller or equal to 0, or less or equal to 0. With this, we need to factor it, because again, it's written in the form where I want it to be. So do we have an x we could factor out? No, doesn't seem like it, so we need to apply the factor theorem. We know that a can equal to plus minus 1, plus minus 2, plus minus 3, and plus minus 6. And then b can equal to plus minus 1 and plus minus 2. So then a over b gonna have values like, or sorry, b over a can equal to plus 1, negative 1, negative, plus minus, sorry, 1 over 2, plus minus 1 over 3, and then plus minus 1 over 6. Then we have a plus minus 2, plus minus 1 again, so we don't need to write it down, plus minus 2 over 3, plus minus 1/3, which is 2 over 6. Okay, with these are our test values that we need to use to find where p of x is equals to 0. So p of 1 is equal to 6 plus 1 minus 8 minus 1 plus 2. That is 6 plus 1 plus 2, that's 9, negative 9, that's equals to 0. So we found our first factor, which is x minus 1, and we should write that it is a factor of p of x. Now, since we found our first factor, and it is a nice simple binomial, we could use synthetic division to find all the second factor. So again, let's write all the coefficients. 1, negative 8, negative 1, 2, carry down 6. 1 times 6 is 6, 1 plus 6 is 7, 7, negative 1, negative 1, negative 2, negative 2, 0. Sorry, my voice is giving out. So our next factor, which will say let p1 of x equal to 6x to the power 3 plus 7x squared minus x minus 2. And now we repeat the same steps again. So now we have, is it the same factors that we had before, 6 and 2? It is, except we have no negatives. So we could keep trying these values out. Let's try p1 of 1. We get 6 plus 7 minus 1 minus 2. That doesn't seem like a 0, so that's not right. If we have negatives, so let's try negative 6 plus 7 plus 1 minus 2. That is negative 6, negative 8 plus 8. That's equals to 0. So negative 1 is also a factor. Since we found that negative 1 is a factor of p of 1 of x, it is also a factor of x, p of x. Therefore, we should write that down as a factor of p of x, p1 of x. So it is also a factor. So a factor of p of x. With that, again, we could perform synthetic division. I'm running out of space at the bottom, so I'll move back up top after I solve this exact question. So let's write that. We have our negative 6, no 6, 7, negative 1, negative 1, and then negative 2. Our answer line 6, negative 6, 1, negative 1, 2, negative 2. Sorry, this was negative 2. So plus 2, and that is 0. So our next factor, so p2 of x is equals to 6x squared plus x minus 2. Now, since this is a basic quadratic, what we could do is apply our knowledge of how to factor them. So we're finding a number that multiplies to 12, negative 12, and adds to 1. So those numbers could be 4 and negative 3. So let's write that down. 6x plus x to the power minus 3 minus 2. Now we expand and simplify. So we have 2x, 3x plus 2 minus 1, 3x plus 2. So we get our newest factors, which is 2x minus 1 times 3x plus 2. Those are our factors. So we could say p of x can actually be factored into x minus 1, x plus 1, sorry, plus 1, I don't know why I wrote it 2. 3x, 2x minus 1, 2x minus 1, and then 3x plus 2, right? Plus 2. Now, if you remember, our next step is to set up an interval chart or analyze all cases. So, since I said I prefer using the interval chart method, I actually would like to show you what all cases means at first, because then you'll understand which one is simpler or which one you prefer more. Okay, well, let's begin by explaining what analyzing all cases would mean. So we're focusing on primarily this part over here, right? We're not looking at p of x because we just let that equation equal to p of x. So we have the following brackets as smaller or equal to 0. So what we need to do is figure out or analyze that this could be A, B, C, or D, and when we multiply all of them, we're getting a number that's smaller or equal to 0. For it to be smaller or equal to 0, either 1 out of the 4 need to be a negative value, or 3 out of the 4s need to be a negative value, right? Because if it was none of them are negative or 2 of them were negative, we'll get a positive number. So with this in mind, we need to look at all the cases present. So at first we have, so to have a equal to something smaller or equal to 0, we could have A is a negative, B, C, D are positive, so that's case 1. A is negative, so I'm just gonna write down. Case 2 would be B is negative, case 3 C is negative, case 4 is D is negative, then we have case 5, 3 of them are negative, so it could be A, B, C, A, B, D, A, C, D, or B, C, D. These are 6, 7, and 8 cases. As you can see, those are a lot of cases where we have to analyze each one of them. So we would say, for the first case, x minus 1 is smaller or equal to 0. So x plus 1, or x is smaller or equal to 1. And that's our first case. Then what we would do is we would put it on a number line and see where all of them like interact. So let's see, this is 1. So this is the area that it's covering, and the rest are going to be like over here, for example. And then we have to look at all the graphs, see where they actually all intersect, and that would be our answer. As you can see, this method is extremely long-winded. and you have to analyze so many different variables, which would take you a lot of time. So that's why I want to show you another method, which is the interval chart. For the interval chart method, as I said, what you do is you create a chart. There's a variety of different ways you could set up a chart. For example, you could use the interval notation we learned in chapter 1, where it doesn't include the zeros, which is personally my favorite version since you're saving space, which is that's the version I'll be showing you today. So, but first of all, you could write down your factors here, and this is your intervals. So our first factor is x minus 1, our second one is x plus 1, second one is 2x minus 1, and the last one is 3x plus 2. Then we separate it, and then we write that our final equation, which is f of x or p of x, whatever you let it be, that's our full polynomial equation. So now up here, we need to find the intervals. So our zeros, as we said, was 1, -1, 0.5, and then -2/3. So our smallest one, our smallest one is -1. So we could say we're going from -infinity to -1. That's our first interval. Then we're using rounded brackets because we're not including the points, because we know this here would be a 0. 0 is at -1. Then we have our second interval, which is from -1 to -2/3. That's another 0. It's important to write your zeros because when it comes to other types of functions, for example, rational, instead of having a 0 at these intervals, we might have a vertical asymptote, if you remember what that is. And if we have a vertical asymptote, it's very important to understand that we're never going to reach that point. But here, we do reach the point, but the value of the function is 0. Now from -2/3, our next smallest one is 0.5, so you could write -2/3 to 1/2. Then we have from 1/2 to 1, and then lastly from 1 to positive infinity. This is our full interval chart. Now, as I said, we need to find a value, or a test value. For -infinity to -2, we could choose something like -2. Here we could use like -0.75. Here we could have like 0. Here like 0.75. And here we could have 2. So -2 minus something will always be a negative. -2 plus 1 will also always be a negative. -2 times 2 minus 1 is always a negative, and -2 times 3 plus 2 is also always a negative. So in all these cases, we have negative values. For 0.75, I like to go across the chart like this, but again, you could just write down your answer first. For -0.75, this is a negative. This, however, is already a positive. This is still a negative, and this is still a negative, because otherwise our notation wouldn't work, you know? For 0, this is a negative. We're just looking at these values. That's a positive, that's a negative, that's a positive. Pretty easy. For 0.75, this is still a negative, this is a positive, this is now a positive, and this is a positive. For the last one, all of them are positive. As you can see, usually from all of these intervals, you are actually adding another plus symbol. Just because we passed 1 0, and from 1 0, of course, we're gonna go up. Now the important part is to multiply all the intervals or all the values, quote unquote, we just got. So 4 negatives are equal to a positive. 3 negatives plus a positive, that's a negative. 2 negatives and 2 positives, that's a positive. 3 positives is a negative, that's a negative. And all positives, that's a positive. Oh wow. So that's the behavior of our chart over here. So essentially we're a positive, then we went below the axis, then up below the axis again, and then we went up there. Something along the lines of this. Right? Like that's positive, that's negative. That's about what we have. It's not going to be that exact form, but whatever. With this in mind, we can answer whether it is smaller or equal to 0. Since we're talking about it being equal to 0, we actually need to remember that we had a 0 at negative 2/3 and a 0 at 1. Therefore, p of x, or f of x, whatever you want to say, let's say p of x over here, because that's was the value we were using before, is smaller or equal to 0 when x is between negative 1 greater or equal to x to negative 2/3, and we also have it from 1/2 to x to 1. That is our solution. If you want to prove it, we could again use the graphing method. Okay, so I just graphed the function and this is what it looks like. Now I made sure that our factored form was identical, so we did everything correct. That's good. Next, we said that it's greater or smaller or equal to 0, and that's the answers we are getting. So what we could see is that our intervals are between negative 1 and negative 2/3, between 0.5 and 1. Is that what we got for our answer? Negative 1, negative 2/3, 1/2 to 1. That is correct. Therefore, this is the full solution for this question. With that being the case, we are done chapter 2. I've assigned a little bit of homework for this chapter, which is 2A, 3B, 4D, 6AC, and 7. It should be around I think 8 questions or 9 questions in total that would test your whole knowledge of how to factor a polynomial function, how to find its zeros, how to set up an interval chart, and then analyze it, and finally find the solution for the inequality. If you follow the steps I just showed you, you should be set for your evaluation, whatever it may be. The one important thing that I want to say is that I know some teachers are extremely picky about it being when you write the solutions for an inequality. For example, I think I put and. Most teachers say that's wrong and you have to put an or. That's what your textbook uses. That's what you should put down too. I sometimes forget to do that, but try not to make the same mistakes I do. Again, if you have any questions, feel free to contact me. But that finishes our knowledge for chapter 2. As you could see, it was primarily rather straightforward, just a lot of steps to follow, and it really just builds on your basics of chapter 2.1 and 2.2. This also concludes our work with polynomial functions in general for this unit, or until we start combining various types of functions in chapter 8. So you could finally relax from our cute little zigzaggy graphs, because next I think we have our rational equations and functions, which should be a lot of fun because we're getting back to our asymptotes and those behaviors. But again, it's nothing difficult. I will be doing it with you no matter what happens. I hope that you had learned a lot from this chapter, and thank you for listening. Have a wonderful day.